A supernova in an expanding universe moves away while it's happening, and light from the end of the supernova has to travel farther than light from the beginning of the supernova. The time of the supernova depicted here is observed as double at the origin. So we say that 1 plus z equals 2 for being double, then z equals 1. That's the measure of time dilation. And this is when the recession velocity is the speed of light. If it were any other speed, it wouldn't be double in this picture. We said in episode 4 that the recession velocity is c at the cosmic turnaround, and that's at z equals 1.6, so time should be stretched by 2.6. Well, which is right? The model is right. This picture is wrong. And we're going to talk about that today and the real reason for cosmic time dilation. First of all, what is cosmic time dilation? Say there's a big clock on a tower and you have a stopwatch 100 meters away. If both clocks are working right, they should both take an hour to progress at the same time. If you were to hike a mile away and look at the big clock with a telescope, an hour on the clock should still take an hour on your stopwatch. At 1,000,000 miles away, it'll take 5 seconds for light to reach the telescope from the big clock, but since all the light is delayed by 5 seconds, 1 hour should be equal on both. At 1,000,000,000 light years, something different happens. An hour on the big clock takes an hour and almost a half on your stopwatch. Time is stretched by a factor of 1.4, so z equals 0.4. Astronomers can use type 1a supernova as big clocks. We could say that the beginning time is at max brightness, and the end time is when the dimming starts to slow down. That's about 20 days. So when a supernova happens 1,000,000,000 light years away, it will take 20 days on a nearby clock, but it'll take 28 days through our telescope. This stretching of the duration is called time dilation. You may have heard of time dilation and special relativity, but they're not the same here. Relativistic time dilation comes with length contraction, and cosmic time dilation doesn't. Special relativity also breaks down at the speed of light. There's this gamma function everywhere, and when v equals c, you get a divide by 0, which you can't do. So what's really happening? Imagine a runner that can run at 1 meter per second is on a track of 10 meters. It'll take 10 seconds to run the track. But imagine this track has a special property called the Hubble flow, and it adds to the runner's speed plus hd, where d is the distance it's ran. The farther it's ran, the faster of a boost it will get. Now imagine a second runner has a delay of 1 second. So after 1 second, the blue runner is this far ahead. It's 1 meter. And because the speed boost is given proportional to the distance, its speed boost will always be greater than the red runner's speed boost, so its lead will increase. But the red runner does everything the blue runner does just 1 second later. So there is no time dilation as they start and finish 1 second apart. Now imagine the finish line is also part of the Hubble flow, and it's moving away at hd. Now the racers will get to the finish line about 2.5 seconds apart, and that's the time dilation. To show you an even clearer view of what's happening, imagine there is no Hubble flow at the beginning or the end, just when the two runners are both running. When that happens, we'll see that there's still time dilation as they finish about 2 seconds, a little bit more apart. So when the race is 10 seconds long, or 18 seconds when it's expanding, and the delay is 1 second, you get about a 2-second delay at the end. In the case of the supernova, the start and end are about 20 days delayed, and the whole trip could be billions of years. So 28 days out of 1 billion years is almost nothing. The motion of the galaxies when the light is emitted or received isn't actually significant in the time dilation. It's caused by distances increasing during the trip. You may have heard that time dilation in supernova proves the existence of dark energy. Well, that's close. A time dilation happens in an expanding universe with or without dark energy. Z is the measure of redshift and time dilation. Time dilation in supernova extends measurements to higher redshift because supernovae are so bright and can be seen from so far away. Our model doesn't fit the measurements without dark energy. You can see more of this in episode 2. So, the specific amount of time dilation measured in supernova proves the existence of dark energy. You may be wondering, what about that z equals 1? At z equals 1, time is dilated by a factor of 2. It seems that should be related to the speed of light somehow. Well, in an exponentially expanding universe it is. When the expansion rate is static, the speed of the galaxy at z equals 1 will be the speed of light. And that's today. When the light was emitted, it will be half the speed of light. Because at z equals 1, everything is half or doubled. That's just how that works. In the standard model of cosmology, we have a dynamic expansion rate. And because the expansion rate's changing, there is no nice relationship between the speed of light and the speed of the galaxy at z equals 1. So, cosmic time dilation is a stretching of the duration observed. It happens because of changing distances, not because of motion. It's not the classical Doppler effect, and it's not time dilation special relativity. It's not dependent on dark energy either, as it happens without it. So, with all that said, is any of this real? I used an asterisk and the in an expanding universe throughout the video because I don't actually believe in an expanding universe. I mean, maybe, but if the universe is not expanding, why do I think time is dilated? Because time was slower in the past. It is literally what it looks like. Check out episode 1 for more information on that, and subscribe to see it in future videos. Have a correction? Have a suggestion for a topic to cover? Leave a comment, subscribe, and thanks for watching.